start. So, happy Wednesday, everyone. My name is Bob Laramie. I'm coming from the Computer Science Department, where we teach data visualization as a full-length module. This is the postgraduate skills development class on data visualization. I guess everybody knows that already. So before we start, just a few things. If after this module you're interested in learning more, there is a valuable resources available to you. So if you can find my webpage, Robert Laramie, you can Google my name, Robert Laramie, and find my webpage. And then click on this amazing photo. Well, you don't have to. You can get there any way you like. We have a DataViz YouTube channel set up, so it's just, you know, if you type my name into YouTube, you'll also find it. So it's a DataViz YouTube channel, and if you click on playlists, you'll find different things like data visualization skills development videos, right? Data visualization event talks, research videos, and data visualization lectures. So the data visualization lectures for the full module, which is 20 lecture hours. So if you're interested in learning more afterwards, you can visit those and see the tutorials and all that stuff. Also, we have a kind of attendance register to see who's here. So if you could just sign put down your name and your department and what you're studying and all that stuff here, that would be really nice to have some idea. Does anyone have any questions before we start? So the layout or the program is somewhat as follows. We give sort of a very generic introduction to data visualization, and then there's a special slide that can go into nine different directions, 9 different examples, like case study examples. And I'm actually going to be asking you guys which one of those case study examples you'd like to see. We can't look at all of them. We can look at maybe 2 or 3. So I'll ask you guys which ones you'd like to see. Then we'll have a little break. And then we'll do an applied hands-on exercise where everybody is led through the process of creating something step by step. If anybody's curious, the software we're going to use is called Tableau Public, and it's on your computers already. So, but we'll go through that step by step in the second part. Does that sound exciting? It is very exciting. It is. DataViz?
Yes.
Yes. Okay. If anybody has questions, just let me know, interrupt me anytime. That's fine, I don't mind. I like being interrupted, actually, for some crazy reason. Oh, there's one other announcement, that's why I have a slide. We have a conference that we're hosting on September 13th and 14th, also over in the Department of Computer Science. It's called the Computer Graphics and Visualization Computer Graphics and Visual Computing Conference, or CGVC 2018. And you might be interested in attending that if you want to see more state-of-the-art DataViz examples or research directions in data visualization. We are planning, we haven't organized that training session yet, but we're hoping to have more training there as well. So you can find that webpage also from my webpage. If you click on Computer Graphics and Visual Computing 2018, so that's the 13th and the 14th of September. So there it is, 2018. It would be good if you could convince your supervisors that you need to attend that conference. It's very cheap. It's only £100. Like, that's the cheapest it's ever gonna. That's the lowest registration fee in the world, essentially. So, okay, let's dig into the material. So this is a diagram. This is a funky diagram. It's a diagram of something that's occurring inside of your head. It's a little bit like a combination of a psychic exercise with science, like combined. So you didn't know that this is going inside in your head, but it is. I'm here to tell you that it is. And it's going on inside the heads of everyone or the society. It's a collective, ubiquitous pattern of thought drawn as a diagram. And it has 6 pieces, so to speak. So it starts with a real-world challenge. Right? We're all here because we have goals. Right? You all have goals. You all want a PhD, right? Or maybe something similar like that. So that's a common mindset. I have some goal, or I have some understanding I'm trying to obtain. That's why you're here at this class, because you're trying to obtain some understanding of data visualization. You might have some other real-world challenges, like you're trying to build something, right? Maybe you're trying to build a house, for example, or a car, or you have some challenge you want to overcome. Right, so that's a very common scenario, right? We start with some goal we try to reach, or something we're trying to build, or some challenge we're facing in the real world, right? It's getting from point A to B, very, very common, right? And for all of our real world challenges, there are real world solutions, also known as, here they're called physical or analog solutions. Right? If we use the example of building a house, we know it is possible for us to build a house, right? If we assemble all the raw materials and we get the tools, the hammer and the nails, we know it is possible to build a house, right? How do you know it's possible to build a house in the real world? Anybody want to answer that question? Because you live in it. Exactly. So you know it's possible. That's just one example, right? You can think of many examples. However, if I asked you literally, please build a house, you know it's possible, but you would find it very challenging. You might say, no, that you know it's possible on the one hand, but then if I said, please build a house, you would say, that's impossible. And I would say, why? And you'd say, oh, I don't know how to build a house, or I can't afford to build my own house. It would take me too long, and so on. So that's the third stage of this pattern of thought. It's not very feasible all the time. In many, many cases, to implement your own real-world or physical solution. Right, so those are the first 3 stages. We have a real-world challenge. We know there's a solution, a real solution. But we also know that many physical or real-world solutions are very difficult because they're either too expensive, usually they're too expensive, or they cost too much time, or they're just not very feasible. Right, that's very common. Everybody follow me so far? And that's true about any problem, challenge, or goal. So then there's a special dashed line. So the left side of the diagram is the real world, and then the right side of the diagram is the digital world. Not that it's not real, but it's the digital world. If I asked you to build a house in software, it would be a lot easier, right? It would be faster, it would be cheaper, and it would be feasible So that's what the right side is, coming up with digital solutions to our problems, challenges, and goals to make the solutions feasible. So if we can do things, solve problems, build things, obtain new understanding using software, right? Because it's cheaper, and easier, and faster. So we transition to the right side, and we all know that. We all know that already. We're already trained to believe, oh, there must be a piece of software that can help me with this problem. It must exist. And if it doesn't exist, people try to just start their own companies to build that software and make it exist. Right? The number of apps that are released every day is, I don't know, a lot. Anybody know the number? I don't know, maybe 100 or something. There's an app for everything, right? That's the digital world, providing digital solutions. And then the consequences of all those digital solutions is what I call data chaos. So all those pieces of software, right, desktop or apps or any digital software might produce a lot of data. Most of them produce a lot of data. Right? The CAD software that builds houses produces a lot of software, a lot of data. And the next slide describes lots of examples of data being generated by digital solutions. So all those digital solutions generate data, but what happens is the data sets that they generate become very large and complicated, or even chaotic. And that leads us to a new problem, right? That's the data chaos problem. And then the final step, which is also something you already know, is that the visualization is the way forward in managing the data chaos. That is the final step. We know that visualization is the tool that we can use to somehow address the problem of data chaos, large, complicated data sets, trying to understand them. So that's the 6 stages. Was it a good psychic reading? It's a psychic. I just did a collective psychic reading. Now you know that's happening inside your mind. It's not just your mind, it's everybody, everywhere. This pattern of thought is occurring everywhere. Right? How many times have you heard people say, oh, I'm going to develop a piece of software for this? Or have you seen this app? Or, that sort of thing. Now, you might not have been fully conscious of the data chaos aspect, but the next slide will make it very, very clear. This is just a list of examples, like the kind of people and the sources of data chaos. Anybody here from engineering? Yes. So you know that in the engineering discipline, lots of people are performing simulations, right? Computational fluid dynamics simulations or any kind of simulations. And they generate massive amounts of data, endless amounts of data. Is the attendance register still going around somewhere? Any physicists? Anybody from physics here? So physicists generate endless amounts of experimental data and imagery, like things like telescopic images and satellite images, just endless amounts of images, just endless. Any biology, marine biology? So you know that the marine biologists and biochemists are generating endless amounts of data with their sensor devices and their other simulations and experiments. So anybody from psychology or sociology or criminology, one of those areas, they generate endless amounts of data too in the form of surveys. Actually, somebody in the business school said, can you help me with my surveys, like visualizing the survey data? This is so typical. So they collected something like 8,000 surveys, and they did, when you have 8,000 surveys, you have no idea where to start, right? And I said, sure, I can help you with that. But are they digitized? she said, no, they're still in paper. Like, oh, sorry, I can't help you. So that's a good example from the previous slide, right? Trying to go from the real world to the digital world. A digital solution would make more sense if you then collecting 8,000 paper surveys, but that's just the way it was for a long time. Sports, anybody from sports science or sports engineering? They also generate endless amounts of data. Anybody know what that data is? Everybody here watches sports, right? Sports games.
Statistics.
They generate statistics, but there's an even bigger source of data for them. Statistics. Statistics are summaries of the actual raw data. So the raw data is video footage. They have endless videos. Right? Of course, journalists and anybody from the humanities at all. Okay, which
Translation.
Translation. Okay, good, perfect. So you know that people in the humanities have never-ending text data. Right? Just go to a library. That's all data, right? Every letter in every book is data. On the left column, those are just examples from the professional world, like professions or career-oriented examples. And on the right side, more personal or individual examples of endless data chaos or sources of endless data. Whenever you go to a bank, right? Whatever you do at a bank, that data is recorded. Every transaction you make at any bank for your entire life is recorded, right? By everybody. Every time you pick up the phone, right, that data is recorded. Every time you use your phone, make a phone call. Sometimes the whole call is recorded. Like every time you hear, oh, this call may be monitored for customer training purposes or whatever. It's just Big Brother trying to watch you. Anyways, every call is recorded. Every time you go shopping, right, somebody's watching you. Every financial transaction is recorded somewhere in a database. Right? And there are people actually watching you, right, with CCTV cameras and stuff like that. But in reality, nobody does anything really with the CCTV footage. Every time you visit a website, right, that data is recorded somewhere. Right? Every time you take transport, right, buses, trains, cars, well, maybe not walking, but every time you take some sort of motorized transport, that data is recorded. Every time you visit a healthcare service, right, data is being recorded about you, and so on. I think you get the idea, right? There's lots of data. Everybody's collecting lots and lots of data. And you are also collecting data personally, right? Your phone, you're collecting data on your phone. You're collecting selfies, right? Like 10,000 selfies on your phone. And those sorts of things. You have a laptop with lots of data, so you're collecting it yourself. Is anybody here collecting it as part of their PhD, collecting data? What data are you collecting?
I've got various digital survey data, text qualitative interview data.
Good, good.
And document analysis.
If you guys have conversations with your supervisors, some of your supervisors will have been collecting data for many, many years, and they're hoping that you can help them with that. Like some supervisors will collect, I don't know how long it took to collect 8,000 surveys, but it was certainly not a week. And it was probably something like 10 years or something. Anybody know what data visualization is already? Anybody have some idea? I have the magic sheet. What's your name?
James.
James. Medicine. What do you think it is, James?
Providing different visual representations of something abstract like data sets in different forms.
Yes, that's a good definition. Did you sign this? You did. Okay, good. That's a very good definition. So it's using computer-generated images to depict data, right? Making a graphical image of some sort of numeric or text, typically numeric or text data. And another way I like to explain it is by comparing it a little bit to computer graphics, because everybody knows what computer graphics is. Who wants to say what just general computer graphics is? Anybody have some ideas? What do you think of when I say the phrase computer graphics?
Using computers to generate images encompasses the hardware and the software.
Do you have any associations? Like, what's the first thing that pops into your head when I...
Video gaming?
Video games, exactly. So you associate computer graphics with video games. Anything else? I think something else too. I'm sure that some of you are thinking, because I can sense the signals, but you're just too afraid to say. Okay, I'm gonna be really exciting here and call some names. How about Julie King? Julie, what do you think of anything else besides video games when you hear the term computer graphics?
I'm not quite sure. It's just.
Have you ever seen a movie called The Titanic?
I think so. Yes. Vaguely remember.
Isn't that the most popular movie in the world or something? Is that the most viewed movie in the world? Anyways, movies.
Right.
Movies.
I
Computer
can see
graphics
photos.
movies. Everybody knows. Lord of the Rings, right? Star Wars. So computer graphics is usually, people like to think of video games and movies, and that is fantasy. Using computers to generate images that are fictional. So database is using computers to generate images that are non-fictional. So they're supposed to depict reality. That's the way, that's sort of the way I like to explain it. So we're going from the world of fiction to non-fiction, or at least we're trying. It is obviously possible to generate fictitious images, but we're trying not to do that. So data visualization is good for exploration. That's the case where you don't know what your data set is necessarily. You don't know what patterns are there. You don't know if there are outliers, and you're just trying to figure out what the data set is and what it looks like, and trying to get an understanding, just some initial understanding of it. That's what we're going to do, by the way, in part 2 of this today's lesson. It's good for analysis. That's if you already have some knowledge about your data. Maybe you're the one that collected it and you're kind of an expert, and you want to confirm a hypothesis or refute a hypothesis. So that's called analysis. So you can use data visualization to analyze data. You can use it for presentation, and that's what I think most people think of when they think of data visualization, presentations. and I'm going to use it now. So I'm using it today, but I haven't done anything interesting yet on the presentation side. So that's when you have done your analysis, already finished your exploration, and then you want to communicate that to a greater audience. And then two more aspects or good advantages that Viz offers that aren't so obvious are acceleration. So you can do some things much, much faster, or some things that are impossible if you use data visualization than not using it. So for example, searching for something. If you can generate a picture of your data, searching becomes extremely fast. Anybody ever play Where's Wally? Anyways, that's not really a great example, but if you see an image and I say, please tell me the maximum value of the data in this image, you'll be able to answer that question in a second. If I just give you a spreadsheet with a million numbers on it, and I take away the Control F functionality, you'll never find the maximum value. Never will. Another subtle aspect is increasing confidence. So you can use data visualization to convince yourself that what you're doing is correct and you're not making errors. And that is very, very common. Very common. So it's very typical that when I get a data set from somebody else, they say, please help me with this. The first thing we do is we discover errors in their data, and then they say, I hate you, Bob. It's also called validation. In the School of Medicine, for example, they call that validation. So increasing confidence. Okay. So now that was the brief introduction to data visualization, and I thought it would be fun to go into different examples or case studies. These are real, so to speak, real case studies and real examples of data visualization software that we built based on that pipeline. So it happens, regularly that somebody in the world comes up to me and says, Bob, I've spent the last 50 years of my life collecting data, and now I am paralyzed as to what I should do. I cannot extract the knowledge that I thought I would be able to extract from my data. Can you help? And I just say, no, I can't help you. Go away. No. And we try to help people, and these are all people that we've tried to help. What we'll do is I'll just briefly describe the different examples, and then I will ask with a show of hands which ones you'd like to see, and whichever one gets the most votes, we'll look at that one, and then whichever one gets the second most votes. And if there's time, we'll do a third one. Okay, science and medicine. Medicine. Okay, lots of medicine. Okay, the first top left is from physics. It's not the world's most popular topic. It's the study of foam. So there are people that study foam and the behavior of bubbles. It sounds very niche. Actually, it is very niche. But it actually turns out to be really, really important because we use foam every day in our personal lives and in our industry. So they generated lots of foam simulation data that describes the behavior of foam, and they asked us if they could help us visualize that. The next example is from the biosciences, marine biology. So the marine biologists, some of them at Swansea University, attach little sensor devices. They go out into the wild and attach little sensor devices to actual living creatures like turtles and cormorants and penguins. Then they release the animal for a few hours or a few days. They recapture the sensor device, and then they bring that sensor device into the lab and try to figure out what the animal did during the time they wore the sensor device. So they asked us if we could help them visualize the data that they collect. It collects like accelerometer data, temperature, pressure, ultraviolet light, and a few other properties of the local animal environment. Another example is from business. I don't see anybody from the business school here, but everybody makes phone calls. So we're working with a company that writes software that collects all the events that occur inside a call center. So every time you call, who calls, when they called, which choices they made in the interactive voice recognition software, how long they were waited in the queue to speak to an agent, which agent they spoke to, what the resolution of the call was. Right? And some call centers get 100,000 calls every day. So they collect that data, and they know that they struggle to understand it. So they asked us if we could help them understand it. That's what that example is. Sports visualization. Right, there is a Welsh rugby union. Anybody here watch rugby? The Welsh. Anybody heard of the Welsh rugby union? I don't watch rugby. You'll have to explain it to me sometime. But as I mentioned, they watch videos to try to understand their opponents and develop strategies. And you can imagine that that's not very time efficient, and it's very difficult. Imagine trying to watch 10 games or any number of games and try to extract patterns from that and the important events and the important behavior. It would take a long time. It would be very difficult. So we worked on some visualization for that from video. Healthcare. So we know that our health data is collected, and we know it's stored in a database. And it's quite a large database, right? Because we're all visiting the doctors, and there's a lot of data being stored in. It's anonymized, and then in some cases it's released to the public. So Public Health England releases anonymized healthcare data, and it's very complicated and big and hard to understand. So that's another example we work on. Computational biology. Anybody heard of computational biology before? That's the study of the motion of atoms and molecules in software, right? As a digital solution. So that would be the right side of the, because it's very difficult to study the motion of atoms and molecules in reality, right? Very expensive. So those computational biologists generate massive amounts of simulation data, and they asked us if we could help them with that. This particular group is from Oxford. This is an example from engine simulation. Are there any, what is it called, the people that like to work on cars? They have a nickname. Motorhead. I think that's what they're called, right? Motorheads? Something like that. Any motorheads in the audience? I don't know if that's even the right term, actually. But that is the study of fluid flow through a cooling jacket. Has anybody heard of a cooling jacket before? That's the part of your engine that's supposed to keep it from exploding. Because if your engine overheats it will just explode. No, it doesn't just explode. It's not supposed to explode. But anyways, anybody know what happens to an engine if it overheats? Does anybody?
Just melts and stops.
It seizes, yeah, the metal will melt, and then the parts will fuse together and stops working. So that's the cooling jacket is trying to take heat away from the engine block to prevent it from overheating. This is another example from motor simulation, and that's the investigating the fluid flow inside the combustion chamber of a cylinder. So your engine has 4 or 6 or 8 cylinders, and then petrol or gasoline is injected into the cylinder. It's ignited, and then it explodes. And that happens at sometimes 1,000 times per minute. Right? And that's what generates the kinetic energy that moves the car. And so we have some visualization examples of that process, that behavior. And then we have some generic texture-based flow visualization example. So that's using textures or synthesizing textures that move in the direction of fluid flow, just general fluid flow. And that can be applied to any type of velocity or vector or fluid data. So we have other examples, but we have to somehow, I just chose these because I thought they kind of represent kind of a breadth, of a diversity of different subject areas. And yeah, I thought that maybe there could be some interest. So I'm sure you've been thinking about which one you'd like to see in more detail. So we're going to take a vote now. Anybody, how many people would like to see the physics example? Foam simulation, a very odd, peculiar one. The marine biology. So 3. You can vote for more than one, by the way. That's allowed. The call center example. The sports example, rugby. 1, 2, 3. The healthcare. Oh, okay, 1, 2, 6, 7. Okay, that's a popular one. Okay, what's the next one? Computational biology. The cooling jacket. Not many motorheads in the audience. Combustion chamber. The texture-based flow is. Okay. Well, the first place is clearly the healthcare. We'll go through that one, and then we'll take another vote for the next one. That sound like a plan? I guess it's because there are lots of people from the School of Medicine here. Is that why? Probably. If you're interested, by the way, I did give a talk, a full-length talk on this case study for about a full hour in the School of Medicine in November. And there's a recording of it on YouTube. We're not going to do the full-length hour here, but if you want even more depth and more detail, there's a YouTube video of that full-length lecture. It is a popular one, and I just gave another lecture on this last week at an event called the UK Spa Conference. That was only 20 minutes. There's a recording of that one on YouTube as well. we're going to talk about it now, but if you want the full amazing detail, you're welcome to look at those recordings. Okay. So the healthcare example, before we jump into what that looks like, we're going to take just a minute to introduce this concept of a tree map. Has anybody here heard of a tree map before? Anybody that's not from computer science, I hope that you guys have heard of tree maps before. Nobody's heard of a tree map before. Okay, one person, two people.
Is it like a decision tree?
You could use it for making decisions. You could use it. It's a way of representing hierarchical data. So on the left, we have a hierarchy, just an abstract hierarchy of data. And if we try to represent hierarchical data this way, it is good, but there is a limitation to this style, this graph style. Can anybody imagine what one of the limitations is from looking at that image?
Space on the screen.
The size?
Yeah.
Yes, exactly. What's your name?
Well,
Will. Excellent. We met, didn't we? Yes. You're the representative?
used to be, not
Okay.
longer, but I used to be. Yeah.
You got scared and left. Yes, if you try to visualize, for example, 1 million data items with this representation, it's going to be very difficult. Right? In fact, that is the cornerstone of what data visualization is. In fact, it is trying to come up with visual representations for large data sets. That's our business. Because you already know how to do it for small data sets. If I give you 10 or 100 data samples, no problem. It's like, what happens when the data set gets big? So this is the tree map representation of that same data. So how does that work? This is the root node of the hierarchy, and that root node is mapped to the rectangle, the outermost rectangle, the biggest rectangle. So that's the standard tree map. And then the big rectangle, the root node, is subdivided into smaller rectangles. So this root node has 4 child nodes. There are 2 leaf nodes and then 2 internal nodes. Here's a leaf node with 12, the data value of 12, and that is represented using this rectangle here, and then there's a 12. Right? The 12 is some sort of data, and it's mapped to the size of the rectangle. Then 8 appears here. It's given another rectangle in the tree map, and it's here. This is an internal node. It's the next leaf node of the root, and that is given a rectangle as well, and it's this one. Since this is an internal node, it has 5 children. This rectangle is subdivided by 5, and then there are the 5 children. 2, 2, 2, 3, 1. And the size of those leaf nodes is mapped to the data itself, the leaf node data. Is everybody with me so far? If you do have questions, just interrupt me at any time. And that process continues. Here we have another internal node, and it's mapped to here. It's this one here that encompasses these. So here's an internal node with 6, 8, and 11. So that's this one, the 6, 8, and 11. The 5 appears here, and then the 40, which is the biggest one, appears here. So it's a recursive subdivision. Right? We start with the whole screen space, and then we subdivide the space. Now, how those rectangles are laid out, when there are many different ways to do that, different algorithms to do that, and we're not going to go into the details of the layout process. But the idea is that when you see this, you can interpret it. You can understand it and interpret it and see what it represents.
So, can I ask a question?
Yep.
So you say that you can interpret this on the right without the one on the left?
This particular example is not very easy, and the reason is it's hard to see the relationship between the parents and the children. Right? We do know that the outermost rectangle is always mapped to the root node, and we know that it has a number of children. But in this particular example, all the boundaries or the rectangle borders are identical. So it's difficult to recreate the one on the left from the one on the right. But the next examples, I think you have some psychic powers. Because the examples that are coming up. Oops. This is an example where the padding has been added between the rectangles, the parents and the children. So you could actually reconstruct this hierarchy from this tree map, because here's the root node, and it gets the full space, and there's a label as well. There's B10, and then there's a padding around B10. So you can see, oh, B10 is a child of A162, and same with C30. And then D62 is this boundary with some padding and a label, and it's been subdivided into F6, G6, H6, and I44. Right? And there's I44, which is subdivided again. So it's not, well, that's from that example. I just chose that example because it illustrates the idea. It is an old example. It's from 1991. So I'm going to bring up sort of a modern example. Actually, I wanted to give a live demo of new security settings. Let me see if I can resolve that. I ran this example just last week, but you know, these updates that happen and then settings get changed. Let's see. So this is a modern example of a tree map. Anybody want to guess what that is, what we're seeing? That's a tree map of some data. Anybody want to take a guess what it is? I mean, the smart people over here should know. What is the most common form of hierarchical data that you use every single day? Telephone? Why is that hierarchical?
Because you've got a region code, international time code.
Is that encoded in the number? Region code? That's a good example. It's not this one, but any others?
Computer data.
Yeah, your hard disk, the disk on the data on your disk, it's stored in a hierarchy. You have a root folder. There are folders inside the root folder, and recursively, right? So this is a picture of a hard disk, or the data on a disk. The root folder is this outer rectangle, and then every folder inside is given another rectangle until, and recursively until finally we get down to the file level. Let's see if this is, okay, it's almost finished. You can see that there's been some shading added to the rectangles, so they look like they have some depth to them or some height, and you can perceive the individual rectangles, and in fact you can get down to the individual files. And this is the old-fashioned hierarchical file browser, and this is the tree map version. And in fact, this should be running here. It takes a minute for it to generate the hierarchy because it has to read the whole disk. I just forgot to run it before the class started. But if we're patient, hopefully it will come up. I just have to be careful that I don't have any secret files on the disk that I could reveal to the audience by accident. So it's reading all the files now, and that's why it takes some time. The name of the program, if anybody's interested, is called Disk Inventory X, and it's free, so you can download it. And it's very useful because, you know, I use it all the time because I run out of disk space. So if you want to find out what happened to all your disk space, why you don't have any more disk space, this is the most efficient way to answer that question. And there is a PC version available. I don't remember what the name of the Windows version is, but there is a free one. I know there's a free one called Sequoia View for Windows. I don't know exactly the names of the other ones. But it's free and it's really, really useful. I use it. I run out of disk space a lot, so I'm always collecting data. So it's very useful. Any questions while we're waiting? This is also meant to add suspense to the healthcare example, like keep you waiting, like, I can't wait for the healthcare. So it finished reading. Right, there's the tree map, and there are the different kinds of files have been given different colors. I'm going to close that to move this over, hopefully. So that's what my disk looks like, right? And if I hover the mouse pointer over any rectangle, it shows me actually the name of the file that it's representing, that rectangle represents dynamically. And down in the bottom, down here, in the information window, it will show the full path up to the file, like where it's located and how big it is, right? So that's kind of a big file, right? It's an open day talk, right, from the 2016. These are big files, right? They're all videos. These are lectures, DataViz lectures. And then I can look at the smaller files and so on. Those are audiobook files down here and so on. So if I was trying to free up disk space, I would just go to the big files and start deleting them. There are some really big ones. That's the iMovie storage folder. And in fact, that's how I found out that I ran out of disk space, is by using this and discovering that iMovie uses a huge, huge amount of disk space.
Can you actually delete the files directly from the visualization?
I do not think you can delete directly. No, I think you have to go and do it the old-fashioned way. It'd be very dangerous.
Because what I'm thinking is does the visualization actually add any value if it doesn't do that? Because what I really want would be an ordered list of your biggest files. You could just go highlight the half a dozen of them and delete them all at once, I would have thought.
That would be very useful, yes. Yes, it would be. You could just have a list. But it's nice just to be able to see every file, isn't it? See, okay, what are the files? Like, you could never see what all your files are with a list. You could never do it, because there could be millions of them. You'd be scrolling all day. But yeah, you could easily have a list of like the top 10. And there are tools that do that, by the way. You can download a tool that will just show you a list of top 10 biggest files. But I use it all the time. I use it all the time to delete and free up disk space.
Are there mobile versions for the disk inventory software?
I don't know, actually, for like an Android or something.
Yes.
I don't know. That would be a fun exercise to find out if there are Android versions of that. So tree map properties, they're space filling, so they make the efficient use of your screen space. They can represent hierarchical data. That's very nice, right? Because a lot of data is hierarchical. They can represent multivariate data, so data that has more than one variable or more than one attribute or dimension. And they can represent very, very big amounts. What I didn't demonstrate there is there's a hierarchy traversal. So you can move up and down the hierarchy. Let's say you have a folder with 1 billion files in it. You can click on just that folder, and then it will expand to fill the whole screen space and show only what's inside that folder. And you can keep going, right? So you can represent billions of files there. However, there's no geospatial information encoded, generally speaking, in the tree map. For healthcare, it's nice to have some geospatial information so we can see which regions are characterized by which kind of healthcare prognoses. And there's no neighborhood preservation, so you cannot determine who your neighbors are going to be in a tree map necessarily. A very quick introduction to cartograms. Anybody heard of a cartogram before? Anybody know what that is on the left? It's a map of any particular place. So that's a map of the UK, but it's leaving out poor Scotland. And this also has another name. It's called a choropleth. So that's when you take all the unit areas and then you map a color onto the unit areas. It's called a choropleth. Very, very common way of a very common data visualization, right? Something you've all seen before. If you wanted to find out where, like, who has the highest cancer rates, though, it wouldn't be so easy, because look at what happens in London. You can't see anything here. Actually, it just looks black. So that's a limitation of choropleths, right? The densely populated areas get sort of overcrowded. This is a cartogram. So all the areas, the unit areas, are mapped to a uniform shape. It's called a dwelling style cartogram. So that, in this case, the shape is an ellipse. It could be a different shape, though. It could be like a pentagon or a square or a rectangle. And then the radius of the ellipse is mapped to some data attributes. So look at in London. London now explodes, right? It increases in its radius and its value. The most common data attribute to depict in a cartogram is population, like how many people live here in this unit area, and then it gets exploded. And that's probably what this is too, right? Because London got exploded, maybe Liverpool and Leeds and Birmingham and Manchester. And look, Cornwall shrunk because it's not very densely populated. So that's a cartogram. And that's nice because it includes geospace. It's nice to be able to see where things are happening in geospace. It's also very engaging. People like maps, and they like to look at them, and they increase memorability. If you see data on a map, it increases memorability. However, they're not necessarily space efficient. Right? Tree maps use the whole space available to spread the data out. Cartograms are generally univariate, so they depict only one variable at a time, typically. Same with choropleths, whereas tree maps can use an arbitrary number. They do introduce geospatial error, and they're generally not hierarchical. They usually don't represent hierarchical data. So we tried to come up with something that combines the advantages of tree maps and cartograms together, called cartographic tree maps. So the idea is they include geospatial information. Every unit area is mapped to a rectangle. Right, that's a unit area right there. They are space efficient because the size of the unit areas expands as much as possible, set by the user exactly, to fill the screen space. They can depict multivariate data. So if I look at one unit area, like this one for example, it's subdivided into different rectangles, and each rectangle represents a health prognosis or the prevalence of a health, typically a health disorder. And if I look closely, the first rectangle represents the prevalence of coronary heart disease for that region. And then the second one represents heart failure, right? So this rectangle, this red one. The third one is stroke, the prevalence of stroke. Chronic kidney disease is the next one. Diabetes is the next one. Hypertension, and so on. So these are 14 different healthcare disorders. And we can see right away, immediately, within seconds, that we have two very prevalent disorders, diabetes and hypertension, right there, the pink and the yellow, that dominate the map. Like they stick out right away. You can see that immediately. So let's have a little look. Now the data we're looking at comes from a place called Public Healthcare England, Public Health England. It's on the web, right? It's public data. Anybody can download it. And in fact, this is an exercise in the full-length DataViz module. This is coursework number 1. Little tip for you. And the coursework is to download the data and try to come up with, use existing tools to depict it. And if you look at the website, that's a typical way of depicting the data on a scatter plot. Right? It doesn't have any color. It's hard to even see what's happening, right, because of all the overlap. And there's no geospace. We don't know where things are happening, right? Which is a pity. It would be nice to see. So let's look at the software. This is another screenshot of the cartographic tree maps. This, by the way, is showing what happens when you click on one of these rectangles. You get an exploded view, and then you get the CCG, or the Clinical Commissioning Group information. Has anybody here heard of clinical commissioning groups? That's how the UK is divided. The NHS services are divided into 209 clinical commissioning groups. So that's a group of NHS services, like hospitals, elder care, GPs and pharmacies and so on. They're all given a clinical commissioning group, which has its own budget. Okay, let's look at that demo. So we have a demo of that. This is what the software looks like in practice. This is work we have done with the School of Medicine, by the way, in conjunction with the School of Medicine. The user can actually adjust the size of the CCGs. So each one of these rectangles represents a clinical commissioning group, that group of NHS services. And the user can actually say, okay, I want the maximum size of each rectangle to be this. And that has consequences, because the bigger the size is, the more space it fills, which is good, but then the more the map is distorted. So the user has control over the space-filling properties and the distortion of the map, right? You can see that the north gets squashed and then spread, and the south gets squashed and spread out. But the good news is that London and other places get expanded, so you don't need to you can see every single clinical commissioning group. And these are uniform size, and that's so that they can be compared easily, like two clinical commissioning groups can be compared to see which one has a higher cancer rate. Here, the clinical commissioning groups are mapped to the size of the population. So we can see, for example, the biggest one is actually down here in Cornwall, the biggest clinical commissioning group. This explosion, by the way, is London, so the population of London being spread across a wider screen space, so we can see what's happening inside of London. And there are a number of different user options here. This is grouping, creating a hierarchy of CCGs. And the more we create a hierarchy, the more it starts to resemble a traditional tree map. That's the user clicking on one of the areas and then getting the details. Right, these are some other user options. Now we mentioned geospatial error as well. So we can actually measure the geospatial error in this. So we measure geospatial error by neighbors crossing each other. So if a neighbor that used to be on the southeast side changes to the northeast, then we count that as an error, so to speak. And we can actually measure that. But the layout algorithm guarantees that no neighbors get swapped. Like a western neighbor will never get swapped to be an eastern neighbor. It will always stay relatively west, for example. And the user has control over the amount of error they're willing to have in their final image. And that's what this little window is. It's reporting the error in the geospatial representation. We can actually show the error, right? And that is, we can use edges to actually show when two cross, their relative positions cross. So generally speaking, but they're far away from each other when they cross their positions. We're not too concerned about the nodes that are far away from each other, because usually we want to compare nodes that are right next to each other and preserve their relative spatial positioning. We have different kinds of color maps, right, and different kind of settings that we can play with. That's the max size setting. These are all the user options. These are some of the different color mapping options that we created. So that's a color map with 14 unique colors. And this one has redundant colors. That's adding some shading to the color maps, similar to the Disk Inventory X program. And some of you are probably thinking, wow, that's a lot of data. It's hard to see what's happening. Therefore, we have filtering options that let the user select subsets. For example, show me all the CCGs that have higher than average diagnoses. They can just click, show me all the higher than average values. Or show me all of the lower than average values. And then the ones that are not selected disappear, or they serve as context information. That's the user choosing individual diagnoses as opposed to all of them. So the user can select individual ones and focus on just individual prognoses. Right? That is diabetes only. If we want to look at just diabetes, we can do that. And if we look at mental health, the mental health of London is a little bit worse than the general populace. We knew that already, though. You go crazy if you live in London, right? and so on. So we can make some observations like hypertension and diabetes. Bradford, for example, has the highest rate of diabetes. Nottingham Northeast, the CCG, has the highest chronic kidney disease. Some of these things, these observations are very easy to make as soon as you can see it on a cartographic tree map, for example. Like Islington has the highest mental health disorder prevalence, and so on. But you can see things about regions, like this is London, right? So it's clear that there's something different about London when it comes to mental health. Like that's an observation you can make with these. However, if we just turn on above average for all the prognoses, London is actually, in the grand scheme of things, healthier. It's only in the mental health category that they're below average. But if we look at all the variants at once, in fact, the population of London is healthier. Lower diabetes, lower chronic kidney disease, lower coronary heart disease, and so on. So that's the below average filter, right? These are all below average prognoses. Any questions about that example? I know some of you are wondering actually, because like I'm getting psychic readings. Some of you are wondering, where can I see that example? Can I watch that in my, like, later? Right. The answer is yes, that video is on YouTube as well, in the research videos, if you want to see that example in more detail, pause it and so on. So I guess I can see that the audience would like a little break. So maybe we take a 10-minute break. What do you guys think? And then maybe we go to the second half, the hands-on, using software to do stuff phase. Does that sound like a good idea? And some of you are also wondering, well, what about the other examples? Like, I really wish I could stay here for a week and get the whole 9 examples. They're all on YouTube. All of the examples are on YouTube. And for most of those examples, I have given talks somewhere at some time, at some event, that explain them in detail. I think actually for all of them, like I gave a talk on the rugby one. That's a full hour. It was in China, actually, and so on. So you can find full-length versions of all those examples on the DataViz YouTube channel. Okay, let's take a 10-minute break, and then we'll all get our hands very clean. Or, actually, the keyboards are probably not that clean. Anybody heard of what the most dirty thing in the world is? Like the dirtiest object that you touch in the world? Huh? Phone? No, I don't think it's the phone. I think there's one thing that you touch often that's the dirtiest thing in the world. Like
Door handles, maybe? Door handles.
I don't think it's door handles either. Has anybody else heard this? It's the steering wheel. It's the steering wheel. Because, you know, people, like, you touch the steering wheel, but you never clean the steering wheel. Mobile phone, you do, hopefully, once in a while, clean it. And doors, theoretically, a doorknob will get cleaned once in a while. But steering wheels and keyboards, but never get cleaned. Actually, there's an easy way to clean a keyboard. I didn't learn this until just recently. Anybody know an easy way to clean a keyboard is?
Buy a new one?
This is free education. This isn't even part of the DataViz module. It's really good though. How do you guys clean your keyboards? Nobody ever talks about this. How do you do it, Amia? A brush is good, but wouldn't you rather clean it like cleaner, the way you would clean a table, you know, or a window? Yeah, baby wipes. Baby wipes are really good for cleaning the keyboards like a little bit better. I didn't start doing that until just like 6 months ago. I'm like, oh, why haven't I thought of this before? Some of my keyboards have been really dirty. And I just had to throw them away. Okay, 10-minute break and then we'll